All right, good morning, guys. Welcome to another session of statistics with confidence intervals. Today we're going to be looking at confidence intervals for sample means. So I'm going to put for means, but we're going to be using the t-distribution. I'm going to explain why we're going to be using this one and what it is. And on Blackboard, I posted a video from YouTube briefly explaining kind of the history about the t-distribution. So I encourage you guys to check that video out. I'll try and include it also here on the description link on YouTube. But I also put it on Blackboard. But check it out over there, and it just explains kind of a brief history where the t-distribution came from, why it's used. And so today I just want to go over the PowerPoint and mainly just explain what I want you to get from it, because since I can't be there with you guys, I want to explain it to you. All right, so the first thing I want to cover is, why do we use t-distribution? Okay, so first thing I want to talk about is issues with accuracy. So when we were working on PANIC, the acronym PANIC, we did these 5 procedures, 5 steps. And there was a part there that's called assumptions, right? And so we would check for randomization. So we would check for randomization, we would check for normality, and the 10% condition, right? It's safe to infer that there are at least, 10 times n. And one thing we have to realize is that the margin of error, one point I want to make is the margin of error is non-resistant to outliers. So again, what does non-resistant mean? Right? It doesn't resist change. So if there's outliers in the data, then that greatly affects the margin of error, because the margin of error is dependent on the standard deviation, and the standard deviation is a non-resistant value, meaning if there are outliers in the data, that'll greatly change the standard deviation. Changing the standard deviation greatly changes the margin of error. Okay, so in formulas, when we use the z-score formula, we need to know the standard deviation. But remember, this standard deviation that we're talking about here, the sigma, is for the population. It's the parameter that we need, which is the standard deviation from the population. And we also need to know that the sampling distribution is normal, but for sure we need the standard deviation to calculate the margin of error. But that's not really realistic. It might not be realistic for us, because sometimes we're not given this value, but we have sample data for the most part. In most scenarios, we have sample data which allows us to calculate this, but instead of using this symbol, we use S for the sample standard deviation. And so that's one of the issues that we run into, is that we're approximating certain values. So since we're estimating the standard deviation, the z-star, this is not based on realistic data. It's based on knowing this parameter, but sometimes we don't know this parameter. The reality is, not only are we estimating, we're trying to find the closest value, or the lower and the upper bounds of the mean for the confidence interval, using the confidence interval, but in a way, we're also sometimes estimating the standard deviation. Okay, so what does this change? Well, luckily, just how there's a normal table, there's a t-distribution table. And that's what the video that I put on Blackboard is about, kind of giving a brief history about the t-distribution. And so I'm adding another table to you guys. So before we would use the normal distribution, now we're going to use the t-distribution. When do we use the t-distribution? When we don't know the standard deviation of the population. When we don't know the parameter of the standard deviation. Okay. Now sometimes they'll give us the data and we can calculate the mean, we can calculate the standard deviation. And when we calculate the standard deviation, that means we're using the statistic, the sample data. Okay. So the next thing I want to talk about is what are some changes to the formula? Okay. So we're still drawing a sample size of n, but what changes in the formula? Okay, so we're still using x bar as our kind of our center point, and then we're still adding and subtracting, plus or minus. The thing that changes is that when we were dealing with sample means before, right, remember going back to the first lesson, when we dealt with sample means before, we would use z and we would use sigma. But the question is, what if sigma is unknown? What if they didn't give you the standard deviation for the population? Okay, so then we're going to change two things. We're going to use, instead of a normal distribution, instead of a z table, we're going to use a t-distribution and use a t value, t-table. And it's kind of the same idea, and I'm going to talk about it a little bit, just how we find a z value depending on the percentage of the confidence interval, right? Right, if I have 90%, we look for 0.05 in the table, and we find a z value. So it's kind of the same idea. It's actually a little bit easier for t values. And the second thing we're going to change is, instead of substituting sigma, we're going to be using s. And s stands for standard deviation, but when we use the letter s, it means that it's for the sample. Okay, and these are the two names. So this is called the z interval. This is called the one sample t interval. Okay. All right. The next thing I want to talk about is the t-distribution itself. And so on this slide, we have the following diagram, and it's a t-distribution. And one thing we want to note is that the t-distribution takes into account the differences in variation due to the sample size. The t-distribution is based on the degrees of freedom. So this, the new thing that I'm introducing in this lesson is something called the degrees of freedom. Okay. Now, the formula for the degrees of freedom is basically n minus 1. It's a sample size minus 1. And the thing about the t-distribution is that it's kind of a dynamic graph. You know how the normal distribution was kind of one graph, and it didn't change from that, right? But the t-distribution changes shape depending on the degrees of freedom, the df. Okay, so you see this red curve here? That's for degrees of freedom 3. This blue curve is degrees of freedom 6. And as we keep increasing the degrees of freedom, it gets closer and closer to this black curve. The black curve is when the degrees of freedom is infinite, right? But what is it approaching? What is it getting closer and closer to? It's getting closer to a normal distribution. So in a way, this black curve here is actually the normal distribution. And so the red and the blue curve, and as the degrees of freedom get larger and larger, they get the distribution, the shape gets closer and closer to a normal shape, normal distribution. Okay. And that's one thing to note is, because the question was, what happens if our sample size is too small? What happens if our sample size is too small? Well, that's another reason we use the t-distribution. So we use the t-distribution for two reasons. One, if the standard deviation of the population is unknown. And two, if the sample size is pretty small. And, small meaning less than 30, because remember the central limit theorem states that sample size has to be 30 or more. But if our sample size is less than 30, then we aim to use the normal distribution. I mean the t-distribution, sorry. If our sample size is less than 30, we use the t-distribution. Okay. Let's see. In this next slide, I think it just states exactly what I said a little while ago, that the black curve is the normal distribution, and as the distribution gets wider and wider, the degrees of freedom get smaller and smaller. And the question is why, right? Well, remember, the width of the data is dependent on the sample size. The smaller the sample size, the wider the graph. The larger the sample size, the narrower the graph. And if the width of the graph is getting narrower, what happens to the height of the graph? It gets taller, right? So the reason that the distribution gets wider as the degrees of freedom get smaller is because degrees of freedom is n minus 1. Let me go ahead and write that out there. Degrees of freedom is n minus 1. Degrees of freedom is n minus 1. And so if the sample size is n, then the degrees of freedom depends on n. And so whatever the sample size does, the degrees of freedom will be affected by that as well. Okay. In this next slide, it's asking, will a sample size of 5 or a sample size of 50 give a more reliable estimate of sigma? Remember what we stated a little while ago is that the larger the degrees of freedom, the closer and closer the graph or the data gets to a normal distribution. The larger the degrees of freedom, meaning the larger the sample size, the closer and closer it gets to a normal distribution, right? So I believe and I agree with this statement is that a sample size of 50 will give us an estimate that is closer to the standard deviation parameter, because the degrees of freedom will be 50 minus 1, which is 49, and that's closer to a normal distribution than a degree of freedom of 4. Right, sample size 5, 5 minus 1. Okay. Now, the next thing I want to do is, I mentioned that we're going to be using a t-chart or a t-distribution now, right? So no longer a z-chart or z-table. We're going to be using a t-table. And so what I want you to do is kind of practice finding values on the t-chart, the t-table. And I put a a PDF file of the t-table in your folder on Blackboard. And if you can just download that file and check it out. And so what we're going to do is find what is the t-value for a 70% confidence interval that has 5 degrees of freedom. Okay. So here I'm going to write a little bit of notes. I'm going to put, my degrees of freedom. It's telling me that it's 5. If my percentage of confidence is 70%, what's on the tail? Remember what we said? Let me draw a diagram here again. So remember we said if I have a distribution and let's say this is 70%, then how much percent is left on these two tails? You have 15% on the left and 15% on the right. You guys remember this? So what we need to find out is, well, when we're using the table, we need to know two things. What's the degree of freedom? And what's the tail percentage? So let's look on the next slide. I put the table there for you. And so remember, we were looking for degrees of freedom, 5. So df, look through the values and look for 5. And then we said 70% confidence interval. How much was left in the tail? 15%, 0.15. So where do these two locations meet? At 1.156. So this is my t-value. And if you notice, if you go all the way to the bottom on this column, it's a 70%. So you can either look for the percentage here, or you can do the subtraction where we find the tail percentage, right? 100 minus 70 is 30. 30 divided by 2 is 15. Okay. And what I want you to do next, and on the slide, on the PowerPoint slide, it'll here is an animation, but check to see if you get these same values. So we did this first one together. So try and find these in the table. If you have questions, you can just message me or email me. But try these out. Test it out. See if you're able to find the t-values using the table. Okay. The last thing I want to mention is what another change that happens is the naming of the interval. Okay. So we've seen 3. This is our third interval. And there are, I think there are, well, there's 3 different ones to be learned. I'm thinking about when we deal with 2 samples. That's in the next lesson. What happens if we have 2 samples? Okay. So when I ask for letter N for the name, there's more choices now. Okay, so I'm going to write them out here. So when we're filling out N, from the first lesson, one of the names we can use is a Z interval. And then on the second lesson, we talked about one proportion Z interval. We talked about one proportion Z interval. Okay. And then today's lesson, we're going to be dealing with a T interval. So again, this first interval was from the first lesson. This is from the second lesson. And this is from today's lesson, the third lesson. All right, so it's up to us to choose the correct name. Again, on an AP exam, they're not going to tell you, this is a Z interval problem or one proportion or a T interval. It's up to us to determine what we're going to use. Okay. Usually Z intervals are for sample means, and they usually tell us that the data is normal and we're using a standard deviation. So let's see, let me do it on the next slide. I'll say, one thing I want to note is, okay, for Z interval, a couple of things. Usually the distribution is normal. That's what's called Z interval. This value, sigma, is known. And that's about it. And then I guess I could say here we're dealing with a sample mean. Okay. The other one I mentioned was a one proportion Z interval. This one is usually normal, and we are dealing with a sample proportion. Okay. And then today's lesson is using the T interval. Okay. So here in a T interval, it may not be normal. Here, the standard deviation of the parameter of the population is unknown, and we are working with a sample mean. Okay. So the first interval, Z and T, are kind of similar, right? But they differ in these two situations. Okay. Okay, so that's the difference between the Z and T interval. So these are possible names for the intervals that we're going to be using in the class. And again, there's one more lesson, so there's one more name. Well, let's go ahead and go into the example. Okay, make out example 1 with you guys. So example 1 says, Andre is a waiter in San Francisco. The IRS is doing an audit on his tax return this year. In particular, the IRS wants to know the average amount Andre gets for a tip. Tips in San Francisco are fairly normally distributed. Okay, so I'm going to highlight some things. It says fairly normally distributed. Okay, so you would think, oh, I'm going to use the normal distribution, right? I'm going to use the Z table. In an effort to satisfy the IRS, Andre took a random sample of 8 credit card receipts, each of which indicated his tip. the average of these 8 receipts was 12.35. So another piece of information, sample size of 8. So n equals 8. And the average of these 8 receipts, or the average of the tips of these 8 receipts is 12.35 with a standard deviation of 2.25. So notice, they gave us another value here. 12.35 is the sample mean, so that's x bar. Now, for the standard deviation, did they give us the symbol of the sigma? No, right? So they said the sample mean is this with a standard deviation of this. So this 2.25 is my S. It's not sigma, because what he did is he took these 8 receipts, he got the average, and then he calculated the standard deviation from these receipts. So both of these are from the sample, okay? So I want to highlight that. This is from the sample, and the standard deviation is from the sample. So these two values are both from the sample. So that means because of this standard deviation, we're going to use a t-interval. Because this standard deviation is unknown. Okay? The question is, find a 90% confidence interval for the population of mean tips received by Andre. So we're going to do the same 5 steps. What are those? What's the acronym to those 5 steps? Panic, right? 5 pieces. All right, so let's go ahead and do it. And in this next slide, I know here I'm just using it as a, it's already displaying things, but if you look at the PowerPoint, it'll animate things, it'll animate different letters of the acronym. So first of all, what's our interest value here? It comes from the question, right? We're interested in the mean, the average of the tips he received. So we're looking for the true average of the tip values that Andre received. What's the symbol for the mean of a parameter? This mu symbol, right? So mu is equal to this. The assumptions, A. 1, was the sample random? Was it random? Yes, it says random sample here. The tips are normally distributed. How do we know it's normally distributed? It said it over here. Okay. And then the last condition is the 10% condition, or the independence condition. Sometimes they refer to it as the independence condition. But it's talking about when we make the statement, it's safe to infer the population is at least 80 tips for independence. How do we get 80? Multiply 8 times 10. Okay. The name of the interval that we're using is a t-interval. And to be more specific, right, we only have one sample t-interval. This is the formula. Remember, a couple slides ago, I showed you how the formula is going to change. You can also write it, where can I write it? Let's see. Yeah, I'll just leave it there. Okay, you can also write it like this. Just so we know what is what. So I just put the fraction in a parentheses. So you can write it like this, right? Standard deviation divided by the square root of n. Okay. Notice that we use t, and the standard deviation we calculate from the sample is s. Okay. Now, one thing they mentioned, and remember what's different about the t value, is that we're using degrees of freedom. So the degrees of freedom for this problem is going to be 7. How do we calculate the degrees of freedom? It's n minus 1, okay? Degrees of freedom is n minus 1. So for this problem, how many tips or how many receipts did Andre look at? He looked at 8 receipts. So 8 minus 1 is 7. Okay. So if I go to my table, which I'll pull up here really quick. Okay, so if I go to my table, we're looking for a degree of freedom of 7 and a confidence of 90, right? So we could do it 2 ways again. We could look at the bottom of the table, look for 90%, or we can do what's 100 minus 90? It's 10. Half of 10 is 5%. So let's look at the table here. So looking for degrees of freedom, 7, and we're looking for a tail of 5%. Or you can look down here. You can look at the bottom there, right? So where did they meet? We're going to end up hitting this value right here. So we get a t value of 1.895. 1.895. So that's my t value. Right? That's where it meets. Okay. Okay. So now we should get the following. We should get the following, and then we have this formula here, right? This was the average tip value that Andre got. This was our t value. This is the standard deviation divided by the square root of n, which was 8. Gives us a lower and an upper bound of a tip average. So he averaged approximately between $10.84 and $13.86. And we're 90% confident that this is the true tip amount for Andre. Okay. So in conclusion, right, there's not much change. We're still doing panic. We're just using a t distribution instead of a z table, z distribution, normal distribution. Okay. Yeah, so that's about it. That's my lesson. Thank you for joining me again. If you have questions, feel free to email me or message me on Remind. And then if you guys want to hold another Zoom session, we can do that too, to clarify any questions you have. But yeah, good luck on the homework and stay safe. Have a great day. Thank you.